Okay, here we go. This is the last packet in chapter 25, and this is part 2. We're looking at example 6, example 6, little Freudian slip there. Anyway, partially filled capacitor. So here's the idea. You've got a capacitor, distance d, and it's partially filled with something that's thickness d over 3, so a third of the thickness put in there. And now we want to know what is the new capacitance of the device in terms of C naught. Here's what we do. We now pretend that we have two resistors or two capacitors that are in series with each other. All right, and so the drawing looks kind of like this, right? We redraw this way, where this is 2d over 3 and this is d over 3. Okay, so it's that kind of thing, so you can see that. And so now I add these up. Since there are two, you know, if this is like C1 and this is C2, C equivalent is, you know, product over sum, right? And so what does that look like? Well, C1 is going to be kappa epsilon naught A over D over 3 times, and there's no kappa because this is just the air-filled one, epsilon naught A over 2d over 3 over, and then I add these up, kappa epsilon naught A over d over 3 plus epsilon naught A over 2d over 3. Okay, so it's a little small. Bring this closer. And so then what we do is we simplify, and this thing, epsilon naught A over d, C naught is just epsilon naught A over d, right? And we can see that sort of embedded there. So we're going to get this all in terms of that. As we simplify, you know, d over 3 can cancel out from all this stuff, but we still have these 2's left over. But if I, so what does this end up becoming? This is kappa epsilon naught A over 2d over 3, or rather this cancels out with one of these, so the other one is left there. All over kappa plus 1/2, right? Because the epsilon naught A over d can cancel out with this one down here, or rather both of these, because that could combine to 1, and so that's a common like factor. And so this is all I'm left with. Anyway, continue to simplify, and what we end up with when we take out this, right, ends up becoming C naught, what does that even say? Oh, 3 kappa over 2 kappa plus 1. Okay, but you know, all the algebra aside, the main thing is that we take this and we treat it like two capacitors that are in series. So if you look at example 7, that hopefully now you see, well, that is the two, but they're in parallel with each other, right? So what we do is we treat this now as two capacitors that are in parallel. Right? It's one capacitor that was filled with dielectrics from two sides, but we redraw it this way. And this is a little simpler because C equivalent is, you know, C1 plus C2, and so this is kappa 1. That's it. Epsilon naught A over d. D is the same. That's not changing, except this is A over 2. So I'll put that down there. Plus kappa 2 epsilon naught A over 2d. So when we simplify this, it really just ends up becoming epsilon naught A over 2d kappa 1 plus kappa 2. So this is going to be C naught over 2 times kappa 1 plus kappa 2, because this is C naught. Right? It's an A. Okay, and then example 8 Example 8 will be a little nicer than before, and really just because the distance is ends up being d over 2. So we redraw this, right? Again, so here's kappa 1. We'll call that kappa 1, and this is kappa... Oh, no, this is kappa 2. Let's do this according to the drawing. Kappa 1. And so, again, we've got, you know, product over sum. Because there are only 2, they're in series, so we add them up this way. So this ends up being kappa 2 epsilon naught A over, and now it's d over 2, right? That original distance cut in half. And then kappa 1 epsilon naught A over d over 2 all over kappa 2 epsilon naught A over d over 2 plus kappa 1 epsilon naught A over d over 2. So here, one of these can cancel out with both of these guys, right? Because it's like, and then these can cancel out with one of these. And so all we're left with here in the end, I think, let's see, kappa 2, kappa 1, epsilon naught A, times 2 all over d kappa 2 kappa 1, and so this ends up being, or the d plus kappa 1. So this is c naught, so it's c naught 2 kappa 1 kappa 2 over kappa 2 plus kappa 1. Okay, so that's it. That's example 8. Example 9. This one looks like a lot of fun, right? What do we have here? We've got 3 capacitors, and it's like the capacitors are first in series. Well, let's just redraw the whole thing. So it's like I've got this one over here. So I've got 2 that are in series, and this one which is in parallel with these 2. This is kappa 1. This is kappa 2, and this one's kappa 3. All right, so first we're going to add these up, and then we're going to, you know, add these up, the product over sum thing, and then just add together with this one. Take careful note here, this is 2D, right? This one has distance 2D, and this is D, and this is D. All right, because before we had D and then we were splitting it in half. But here this one is 2D. And the areas, this is A over 2, and these are A over 2 also. So, adding these up, I end up with, right, kappa 2 epsilon naught A over 2 over D times kappa 2 epsilon naught A over 2D. I'm just bringing the 2 from the A down there. And so now, again, down here, these two have the same properties, right? So they're both epsilon naught A over 2D, and this is kappa 2, oh, this is 3, sorry, plus kappa 3. So we've got some things canceling out. We'll cancel this out with these guys, and so this ends up being kappa 2, kappa 3, epsilon naught A over kappa 2 plus kappa 3 times 2D. That's the 2D from here down there. Now I'm adding this with this. So what's this one? This one is kappa 1 epsilon naught A over 2D. Again, right? It's A over 2. Oh, here it's actually, but this is distance 2D, so this is going to be 4 down here. Right? A over 2, and then the 2, if I bring that to the bottom, 2D. So I'm adding this and this one. Kappa 2, kappa 3, epsilon naught A all over 2D, kappa 2 plus kappa 3. So here is C naught there, and here is C naught for that one. So it's going to be C naught times kappa 1 over 4 plus kappa 2, kappa 3 over 2, kappa 2 plus kappa 3. Quick note here, actually that answer is wrong. What it's supposed to have, C naught is supposed to be epsilon naught A over 2D. And so therefore the answer really ought to be, K1 over 2, and then K2, K3 over just K2 plus K3, right? There's a factor of 1/2 that should be embedded in the C naught. So apologize for that. Okay, and that's it. Messy, but that's what we get. No, it's not. I'm going to say we're going to skip example 10. Example 10, we're not doing. All right, so now some quantitative effects when we're adding dielectrics. So same kind of thing as before. There'll be a quiz on this stuff, by the way. What happens to E field, V, all this stuff. So example 11, we've got a capacitor. It's charged, and then it's disconnected and isolated. Okay, so again, disconnected and isolated. What's the constant here? The thing that's constant is the charge. So charge has got to remain constant. And so we've got this chart, C, Q, V, E, and U. But now we've got two things. This is for n less than 1 and for n greater than 1. And so what's the thing that we're altering here? What we're changing is the distance between the capacitor plates, right? So in this case, the new distance between them is nd. If n is greater than 1, that means we're making it more, right? It's getting farther apart. If n is less than 1, then n times d, that new distance, if n is less than 1, the new distance will be they're closer together, right? And so we know, right, they're set equal to each other, so the Q is the same, right? Q is the same because they're isolated. However, since Q equals CV, as I get them closer together, right? If D is decreasing, then or C rather, C is epsilon naught A over D, right? So if D gets smaller, C gets bigger. So that's what happens there. And if C gets, let's just deal with this one for now down here. So if C gets, this has to stay the same. So if E gets bigger, that means V gets smaller. Right? And the electric field, V is ED, right? So E is V over D. But if V gets smaller, but D is getting smaller as well, and by the same amount, because embedded in here is the D, then the electric field is just the same. And U is 1/2 QV. Q is staying the same, but V is going down, and so that means that U is also going to decrease. Now let's go over to this side. Here, if the distance is getting greater, then D is going to go down, right? D goes up, but C goes down. And since C goes down, if C goes down, V has to go up. Those are inversely proportional. But again, if D goes up and V goes up by the same amount here in the electric field equation, you see this will then be the same. But again, now if U is 1/2 QV, Q stays the same, but V goes up, so then the stored energy will also go up. Okay, so that's what happens in that case. Let's take a look now at the other one. So now we're taking a capacitor and we're doing the same thing, except that in this case it remains connected to the voltage source. Since it remains connected to the voltage source, that means that the voltage will be staying the same. And so again, if the voltage stays the same, what happens? Well, C is epsilon naught A over D. So again, if D gets to be smaller, that means that C will get to be bigger. Now Q equals CV, and so if Q is, if C goes up and V stays the same, that means Q is going to increase. All right, now E is V over D, and so here V is staying the same, but D is decreasing. So D decreases, then E goes up. And again, 1/2, if U is 1/2 QV, V stays the same, but Q goes up, and so therefore the stored energy goes up. Now to this side. If D gets bigger, C gets smaller. If C gets smaller, then Q gets smaller because V is staying the same. V stays the same and D gets bigger, so that means E gets smaller. 1/2 QV, Q stays the same. That means that V is going down, or V is the same, sorry, and Q is going down. So that means the stored energy has to go down also. These chart questions, examples 11 and 12, and then the other ones from earlier, examples 1 and 2, I would say know those pretty well. They might show up on a quiz of some kind. Okay, and so now what we want to find is the potential difference between A and B in this last kind of example. And so let's draw this circuit so we can analyze it. So if this thing is 20 volts, let's see, how are all of these connected? These are all connected in parallel to each other, right? And these two are connected in series to each other. And one way we could look at that, let's do this. So if this is the plus and this is the minus, when this is all charged up, then these will have pluses collecting on that side, minus, plus, minus, plus, minus, plus, minus. And so if I go from here to here, notice I'm going from positive to positive, positive to positive. These are all in this and this and this are all in parallel with each other, right? And so the negative is connected here. This is negative. That's the positive, negative, positive. But here I go from positive to negative, and here I go from positive to negative. So these two are in parallel with each other, but in series with this whole thing. What I would recommend then is that and where's B? B is over here, and A is over here. What I recommend is that we redraw this, keeping, so it makes a little bit more sense in terms of how we think about parallel and series. So if I draw this, I have this coming over, and then this one had 3 branches on it, right? All right, so here's A, here's B. So that's what it looks like. It's the same thing. So here's 3, 3. This was 2, 2, 4, and 4. And what we end up finding here is that, right, the equivalent capacitance here is 2, and then 2 plus 2 plus 2, this whole thing has equivalent capacitance of 6, and then these two added up have equivalent capacitance of 6. That means that the voltage, 20 volts, is split evenly between this capacitor thing and this capacitor thing. And that's really what's separating here. So from A to B, it's a 10 volt difference.